Hello, everyone. Myself is Dinesh and my roll number is 536. And my topic is about squeezing deep learning into mobile and embedded devices. Deep learning is a subset of machine learning algorithms that attempts to model high-level abstractions in data by using architectures composed of multiple nonlinear transformations. Deep learning automatically finds out the important features that are important for classification, and deep learning does end-to-end processing. We believe, in particular, that deep learning will play a prominent role in the evolution of smart devices such as phones, watches, and embedded sensors moving forward. The emergence of mobile and embedded forms of deep learning has been slowed by the extreme resource overhead that it can easily introduce. Deep learning model consists of multiple layers which learn the data hierarchically. This is also called as deep learning neural network. Convolution neural network CNN consists one or more convolution layers. CNN is mainly designed to take advantage of 2D input like image or speech. Convolution neural networks can be used for image processing. An image is divided into multiple overlapping grids, which is fed into convolution layers. Sampling and max pooling of the data is done. The output is then given to another neural network called fully connected layer, which finally tells whether an image is matched or not. Most of real-world applications like object identification, speech recognition, natural language processing, video analytics, etc., uses deep learning to provide accurate results. The convolution approach for such applications is to offload the computation and storage on cloud server. Only input and output is processed at the mobile device. This method is useful as deep learning is computationally expensive and it more space to store the data. This method has its own disadvantages when it comes to highly interactive real-time and responsive applications, like if an application has to identify the object in front of the user, it has to process the image and produce the output immediately. Mobile big data is the huge amount of data generated by mobile devices. The data generated by mobile devices are mostly unstructured or semi-structured data. Deep learning models can be used to analyze this data to obtain useful insights about the data. Volume, variety, volatility of the data has to be handled in order to obtain accurate results. The learning of deep models can be parallelized to reduce the time taken for making decisions. The data is divided into several parts and stored in different machines. The learning of deep models can be parallelized to reduce the time taken for making decision. The data is divided into several parts and stored in different machines. Then map-reduced tasks are executed on each chunk of data in different machines. By extending the streamlining capacity with higher bandwidth, the huge data produced every second can be handled. The immediate the intermediate data of map-reduced tasks is volatile. To handle this, the training of deep learning model can be speeded up. The training of the models can be done on GPU supported systems and only inference models can be run on mobile devices. The main bottlenecks to run the inference model on mobile devices is memory and computational energy. To run the inference model on mobile devices, each layer of the model can be compressed at the runtime. The main bottlenecks to run the inference model on mobile devices is memory and computational energy. To run the inference model on mobile devices, each layer of the model can be compressed at runtime. Then the camera captures real-time images and perform analysis locally without offloading the computation of the cloud. The key feature of CNN model is that the execution of the layers follow strict order. Fully connected layer is applied on output of convolution layer. There are two threads that are spawned during execution, one being convolution execution thread and other load thread. Once the convolution execution thread completes, the output of the final convolution layer of each model is passed to the data load thread, which loads FC parameters onto the memory and proceeds to obtain final convolution results. Region-based CNN, also known as RCNN, attains the candidate object regions and convolution networks is independently evaluated for every ROI. Faster speed and accuracy is obtained by extending RCNN to allow ROI on future maps using ROI pool. Faster CNN is a flexible framework which learns the attention mechanism by region proposal network. Faster RCNN is the leading framework in present benchmarks methodology. Mask RCNN is used for object detection and image segmentation. The model is built using mask RCNN. The present working model provides the bounding box for each object instance in the image. The bounding box contains the objects in the images along with a mask. Initially, the model is built using mask RCNN network. The first step is regional proposal network that displays anchor box refinements. Then in next step, the solid bounding boxes are obtained around each object in the image. In the next step, the image is segmented using mask RCNN and masks of each object instance is obtained. Every mask is differentiated with the color of the mask. This model detects the objects and displays the score. For example, person 0.993, which means the object detected is 0.993, that is 99.3% a person. Along with object detection, segmentation of object is also done and mask to the segment is obtained. These segmented object instances can be used for human process recognition and many other similar applications. The model is extended to provide an additional functionality of predicting the relative position of the object in the image. For this purpose, we consider the coordinates of the bounding box obtained from the object detection model. According to the image coordinate system, the midpoint of image bottom line is considered. From the image height, the image reference point is taken to be bottommost line of the image. The camera is supposed to be in front. The camera was taken, hence it becomes sensible to consider the bottommost boundary of the image to the reference plane where the user is standing. Figure 1. Figure 1 shows the vertical distance measurement from plane of reference. Figure 1 shows the image in which multiple objects are detected and they are displayed in bounding box along with their scores. The image also shows the segmentation masks being obtained. The pixel distance of the object is considered to be vertical distance of object from reference plane as shown in figure 1. Midpoint of the bottom line of the image is considered and its Euclidean distance from bottommost line of the image is obtained. Based on the distances, it can be observed that the relative positioning of the objects can be obtained. This method helps to tell which object is nearer and which object is farthest. Thus, it helps to know the relative positioning of each object with respect to the user. Model compression technique is used to compress the image. Every layer in the model is compressed so that it can be run on mobile devices which are resource constrained. With less memory and computational power, the CPU systems must be able to run this model and predict the outputs within a time limit. In figure 2 is workflow and first step is build object detection model using a mask or CNN network. Train the model with 35K COCO dataset and third step is obtain bounding box and scores for each object in images. And fourth step is object obtain object mask for each object segment from mask or CNN. And fifth step is calculate relative distance between objects in the image and plane of reference. And last step is run the newly built model on CPU system. Figure 2 shows the workflow of project being carried out. The initial step to be performed is to get the appropriate training data, pre-process the data if necessary, so as to obtain the information required for the study. Once the dataset is ready, next step is to build a desired model using mask or CNN network. This model has to be trained with the pre-processed data. Once training is done, some test images data can be given as input to the model. The model has to recognize all possible objects present in the image, draw the bounding box around the image, providing class name, information, and scores of each object. Once the objects are identified, the model is extended to obtain relative distances of the objects in the image. The Euclidean distance is calculated, appropriate positioning information of the object is displayed. The obtained model is of a bigger size and may not run efficiently on mobile devices. Hence, quantization can be done on the model and model compression can be performed to reduce the size and complexity of model so as to run on resource constrained devices like mobile. Figure 3 is output of image 1 and figure 4 is output of image 2. Figure 3 and figure 4 shows the output of the model. Figure 3 shows zebras and giraffe in a forest. Below the image, the results are displayed. The result shows the object names and the relative distance of the objects from the plane of reference. The order of object is sorted based on their relative distances. In figure 3, zebra is near most object, hence its distance object is the least, which is 82. The farthest one is under zebra with distance 207. Similarly, figure 4 shows an outdoor image of some group of people standing. In this image, two persons are standing two persons are standing at the same distance, hence the relative distance obtained is same. This shows the object detection and object segmentation along with the scores and distances. Conclusion. In this, we discussed about the advantages and disadvantages of state-of-art application which uses cloud-based systems. It describes how squeezing deep learning into mobile devices can overcome these issues. It describes the various methods available for compressing deep learning models, various optimization techniques. A new model is built over the existing object detection model, which extends the existing model to measure the relative distance of the object in the image. The newly built model performs at 79% accuracy on the CPU system. And that's it. Thank you, everyone.